This lecture is about geometry and computers. Geometry, amongst other things, is about curves and surfaces, and computers are very good at drawing pictures. So there is one obvious interaction between geometry and computers, that things which are of interest to geometers or to other mathematicians can be drawn on the screen, and this can illustrate theorems that geometers have proved, can perhaps suggest new results for them to prove. In the way that I've illustrated on this first slide, that there is an interaction from computers to geometry where we could verify, illustrate or suggest results. On the other hand, there is also an interaction the other way, because geometry, particularly modern differential geometry and singularity theory as developed over the past 20 years or so, is able to give us great detail and to explore in detail the relationship between the surfaces of solid objects and what we actually see of these objects, which is a two-dimensional representation either on the retina of the eye or on the film of a camera or on a television screen. So there is an interaction the other way from geometry to computers. Remote sensing is developing systems which must deduce information about objects from distant views of the objects. For instance, industrial robots have to do this. They have to pick out objects from bins by recognizing what they are from distant views. This, of course, is a severely practical matter, but I shall stay away from the most practical aspects in this lecture. What I shall be doing is to give a rather personal, perhaps even idiosyncratic survey of the kinds of interactions which I have personally been involved in, or which seem to me to be particularly interesting or to have particularly nice pictures associated with them. In the first part of the lecture, I shall go into some detail in one particular interaction where some very simple results of geometry can be illustrated, I think, very dramatically by means of computer graphics. This is the kind of computer graphics which you could do on a home computer so long as it had reasonable resolution, although most of the pictures that I shall show you were done on a high-resolution screen. In the second part of the lecture, I shall just give a sketch of various interactions which seem to me to be interesting, both ways, geometry influencing computers and computers influencing geometry. And this is really an excuse to show you some very nice pictures, some of them produced in Liverpool, where I come from, and some of them produced in other places. So I'll begin by making a simple observation about the relationship between circles and curves. So here we have a curve which I've called C and a point P0 on the curve, and I'm going to look at various circles which touch the curve C at the point P0. The centers of these circles will all lie on the normal to the curve C at P0. This is the line through P0 which is at right angles to the tangent. A small circle will be inside the curve, as you can see in the picture on the left. A small circle will be inside the curve, at least near C, near the point P0, and a large circle will be outside the curve. So as the center of the circle moves up the normal, the circle moves from a situation where it's entirely inside the curve to a situation where it's entirely outside the curve, so long as we look at that part of the curve which is close to the point P0. Let's look at this again in slightly more detail. Now in this picture, as you can see in the left, where we have a small circle which is inside the curve, the distance from the center A to a point P of the curve starts out by being bigger than the distance from A to P0 when P is on the left of P0 as it is there. This is because the distance AP is larger than the radius of the circle. The radius of the circle is equal to AP0. So as P moves along the curve C through P0, the distance will decrease and then increase again. So the distance will have a minimum at P0. On the other hand, on the right, where A is the center of the large circle, which is outside the curve. As you can see in this case, the distance from A to P is now less than a radius because the circle is outside the curve. So the distance AP0, which is the radius, is greater than the distance AP. In that case, as P moves along the curve through the point P0 out to the other side, the distance will increase and then decrease again, which means that it has a maximum. So as the point A, the center of the circle, moves up the normal, the distance from A to the curve starts out having a minimum at P0, and later on it has a maximum at P0. So something happens in between it having a minimum and having a maximum. You can illustrate this by means of a sequence of pictures. Here is a curve. The curve on the left is something like y equals x squared plus a fifth x cubed to make it an unsymmetrical curve. And what we've done is to draw lots of lines out from a point on the vertical normal to the curve. The tangent to the curve is at the bottom and the vertical line is the normal. And this point on the normal is sufficiently close to the bottom for the distance to have a minimum. And you can see this in this picture because what we've done is to take lots of lines out from this point on the normal out to the curve, and then on the right they've been reproduced but vertical. So they've been kept the same length, but they've been made vertical so that you can see how the distance is changing as we move along the curve. The distance from this fixed point on the normal, where all these lines congregate on the left, down to the bottom of the curve there. You can see that there is a minimum of distance. If we start moving the point up the normal, here it's a little bit further up, and you can see there is still a minimum. It's quite a flat minimum. It's what we'd actually call a degenerate minimum. If we continue to move the point up, you can see that minimum is beginning to have a little hump in the middle. So the graph on the right tells you what the distance is doing. And the distance now has, it looks as if it has a tiny little hump there in the middle. And that hump will grow as we move the point further up the normal. So you see now there is emerging a maximum. You can see very definitely there is a maximum in the center. So a minimum has turned into a maximum as you move up the normal. At this point, I should like to do a short calculation, but first I'll just summarize what I've said. There is the curve C, there is a point on it, and here is the normal at this point. As we move along the normal, the distance from the point to the curve is first a minimum, and then it changes over to a maximum. The number 1 over 2a there is something that's going to come out of the calculation, which I shall now take you through on this paper here. What I've done is to draw a curve, y equals ax squared plus bx cubed, and then there might be higher terms, but that won't bother us. A is assumed to be positive. That simply means that the curve is like that rather than like that. It has no effect on the final result. Here is the normal to the curve at this point P0. And here is a general point, 0k, on the normal. What I'm going to do is to examine the nature of the distance of this point from this curve. So I shall write down a formula for the distance. In fact, it's more convenient to write down a formula for the square of the distance, since this doesn't involve square roots in the formula. So here is capital D is the square of the distance, where little d is this distance here. How do we work out the square of this distance? Well, we use Pythagoras' theorem. It's 0 minus x all squared, that's this x squared, plus k minus y all squared, plus this. We now substitute for y. Y is ax squared plus bx cubed, and so on. So we substitute that in the formula. We square everything out, and then we look at the first two terms that come out. The first term is k squared. Well, that's hardly surprising, because when x is 0, the distance down here is most certainly k. So the square of the distance will be k squared when x is 0. The interesting term is the next one, which is an x squared times 1 minus 2ak. And then there will be higher terms. Now what I'm going to do is to plot the graph of this distance. So this is a little bit like the graphs that you were seeing a minute ago, except that here I've done the square of the distance because mathematically it's simpler. There are two cases depending on the sign of this coefficient here. If 1 minus 2ak is a positive number, 1 minus 2ak is positive, that's the same thing as k less than 1 over 2a, then k squared plus a positive multiple of x squared, that looks like a minimum. That means that the function d has a minimum, like this. The graph of a function of constant plus a positive multiple of x squared is like this. Remember, this is the graph of the d function, the square of the distance. On the other hand, if this number is negative, 1 minus 2ak is negative, that's the same as k greater than 1 over 2a, then a constant plus a negative multiple of x squared looks like this, a maximum. So you see this confirms what we did before, that as you move up the normal, as k increases, passes through this critical number, 1 over 2a, the nature of the distance function, equally the nature of the distance squared function, they will have a minimum or maximum together, changes from a minimum to being a maximum. So I just look at another look at the slide. As we move up the normal, the nature of the distance function changes from a minimum to a maximum, and the critical point at which it changes is the distance 1 over 2a. The point along the normal at this distance is called the center of curvature at the point on the curve. It is in fact the center of a circle which is neither inside nor outside the curve. It crosses the curve at the point. Points along the normal which are before this, which have a distance which is less than 1 over 2a, are inside the curve. Points which have their circles which have their centers beyond the point E are outside the curve, and the circle with center E is neither inside nor outside. In fact, it straddles the curve, it crosses it there. I'd like to look at this calculation from a slightly different point of view. So let's look at the curve again. Y equals ax squared plus bx cubed, and so on. And now instead of looking at the distance, I'm going to look at something which is going to turn out to give the same answer. So I'm going to look at the normal here at the point P0 and at the normal at a nearby point, which I've called P with coordinates x, y. So here is the normal at a nearby point. I'm going to ask where they intersect. You might think that if P is very close to P0, the normal at P0 and the normal at P would be almost parallel, so they would meet far up the axis, but this is not so, as the calculation shows. Let m be the slope of the curve at P, the slope of the curve here. So that's the slope of this tangent line to the curve. This is dy by dx, the derivative, and y is ax squared plus bx cubed, so we can work that out. Differentiating this is 2ax plus 3bx squared, and then there may be higher terms. To work out where the normal here meets the normal here is then an exercise in coordinate geometry, or alternatively an exercise in similar triangles, which I won't go through. You might enjoy trying it for yourself. The distance up the normal, where the two meet, turns out to be y, the y coordinate of the point P, plus an extra bit, which is just x over m, where x is the x coordinate and m is the slope. The distance is y plus x over m. So that is the distance up here. Let's see what this becomes when x is very small. So we just work out y plus x over m. Y is ax squared plus bx cubed, and so on. Comes from here. X, well, that's just x. And m is the slope, which is 2ax plus 3bx squared, plus and so on. Now there's an x which we can cancel from here and into the denominator, giving us 1 over 2a plus 2bx, plus and so on. So now let's ask the question, what happens to this when x is very small? Well, all these terms just become 0. All of these terms become 0 except for a, for 1 over 2a. All of this just disappears. So the limiting value of this y plus x over m is 1 over 2a. What this says is that if this normal here is very, very close to this one, if we take a normal round here which is very, very close to the normal at p0, then these two normals will intersect at a point very nearly equal to 1 over 2a up this normal. And that's exactly the same number as occurred in the other calculation. If I just bring that back for a moment, it's exactly the same number, 1 over 2a, which occurred in the other calculation. So this means that this critical point on the normal, just return once more to this slide, the critical point E on this normal can be regarded as the place where minimum turns to maximum, but it can also be regarded as the place where two very nearby normals meet. So each point on the curve has a normal at that point, and on each normal there is a critical point E where minimum turns to maximum, and this can be regarded as the intersection of that normal with very nearby normals. Here is a picture of this where the curve in fact is a parabola. As you can see on the left, here we have a parabola with lots of normals drawn to it, and you can see that these normals, nearby ones, intersect on this cusped curve that comes down from the left, comes down to the point E0, and then goes up again to the right, to the point E1. What we've drawn in this picture is lots of normals to the parabola. Nearby ones will meet, as we've just seen, at these critical points, the centers of curvature, where minimum turns to maximum. I'd like to just point out one or two things about this situation. As you can perhaps see, lots of normals pass through those points inside the cusped curve which are near the point E0. In fact, as you cross the cusped curve, which is the locus of the various points E corresponding to the various points P on the original parabola, as you cross this cusped curve, the number of normals through the point changes by 2. It changes from 1 to 3. You might also see that the radius itself, the distance P1, E1, this critical radius where minimum turns to maximum, in fact itself has a minimum at E0, P0. And that is illustrated here by the fact that the cusp curve actually does have its cusp there. Minimum of radius is turned into a cusp. Well, with a little bit of imagination, not to mention a few $100,000 worth of equipment, one can turn this kind of thing into very beautiful pictures. And in fact, this picture was produced by Thomas Banchoff at Providence, Rhode Island, at Brown University, and you see it is nothing other than lots of normals to an ellipse. And they are intersecting, they're interfering with each other, if you like. They're intersecting at points along this four-cusped curve. The four-cusped curve is the locus of these changeover points, these points E, and this is also called the evolute of the ellipse. Here is a slight variant of the same idea, which looks really quite three-dimensional, but it's really just the same thing. It's lots of normals to a curve. At this point, let's try changing the shape of the curve. If you just change the shape of an ellipse, then you don't get anything particularly interesting happening. But if you take a family of curves which have degree 3, a family of cubic ovals, then you can get some very interesting things happening on this evolute, which is the curve that is picked out by the eye when you draw all the normals to the curve. It's the place where the normals intersect one another, where they interfere with one another. And it's picked out by the eye. It's often called an envelope. And in fact, you can see this on the first video that I've prepared for the lecture. Here we see a family of curves, in fact cubic curves, changing shape, and for each one the computer has drawn for us all the normals to this curve, or a great many normals to it. So you can see for each curve the evolute, which is where these normals intersect one another. It's the curve picked out by the eye with all those cusps. And you can see as the curve changes shape that there is something happening there down in the middle left. Two cusps are appearing, disappearing, and now appearing again. You see the two cusps appearing, and now as we go back, they disappear and the curve becomes smooth. Here we see another family of curves changing shape, and for each curve again the computer has drawn a lot of normals, so that the bright curve you pick out in the middle is the evolute, where the normals intersect one another. And as the curve changes shape, you see now at the right hand end two cusps are forming and disappearing again. Watch it again. At the right hand end two cusps are appearing and disappearing. Also, there's something else happening here, that another cusp at a different point is crossing the curve there and recrossing it. Cusps move about, they migrate around, and at other places cusps form and disappear in pairs. Two things are visible on these videos where you see the changing shape of the evolute as the shape of the curve changes. One is that cusps move about. They migrate across the plane. The other is that pairs of cusps disappear and appear. It's always cusps which disappear in pairs, leaving a smooth piece of curve. If we look at the next slide, then what I've imagined here is that we have a sort of time dimension in which a cusp is migrating about in the plane, but instead of drawing all the cusps in the same plane, what I've done here is to draw them all in different planes, moving from right to left across the picture. So you are to imagine that a cusp is moving in a single plane, but then what we're doing is to stack lots of planes now from right to left in increasing time. So the cusp on the right of this picture is to be regarded as part of the evolute of a curve, and the sections of this surface that you see now, the various sections, will be the migrating cusp as the shape of the curve changes. From right to left, time is changing, just as it is on the video. The other thing that happens in the course of changing the shape of the evolute is that pairs of cusps disappear. And that's illustrated in the sequence across the top here, where a pair of cusps and also a crossing comes closer and closer together and then disappears. We could also move this in a time dimension. We could draw a single surface, the forward end section of which is the two-cusped curve that you see in the left at the top. This has also been transferred down onto this surface as the forward end section. And as we move in the direction of the arrow, we take different sections of this surface, moving from front to back. The different sections of the surface exactly mimic what's happening to the evolute. The two cusps are merging and then disappearing. This idea of stacking the evolutes of a family of curves in a time dimension in order to discover what happens to them was not in fact made formal mathematics all that long ago. In fact, we owe this kind of mathematics to the Russian mathematician Vladimir Arnold, who wrote a very seminal paper in 1976 in which he showed how to find what happens to the changing evolutes of a family of curves. What are the kind of things that can happen to these? And what can happen is, in fact, that cusps can migrate around on the plane and that they can disappear in pairs, as we have seen. If I just look back to the slide a moment, then this transition from left to right, where the two cusps disappear, is called a swallowtail transition. In fact, in the original papers, written by Arnold and his Russian colleagues, they always used to call this kind of happening a perestroika. And at a meeting of the London Mathematical Society in 1988, when Arnold gave a lecture, he said that it was really no longer necessary to translate this word perestroika into English, since it's become a standard English word. So why not just call it a perestroika? It was always translated before as a metamorphosis in the English translations of the Russian papers, or transition is another word. But let's call this a swallowtail perestroika. This is what happens on the family of an evolute, the evolute of a family of curves. To give you a little bit of an idea of the international nature of this kind of work, as is much mathematics, there are people from all sorts of countries who are involved. Here is a little list of credits. As you can see, it goes from A to Z, from Arnold to Zakhalyukin, both of whom are Russians. J.W. Bruce, Bill Bruce, is British. Jim Damon there in the middle is American, and Saito and Tereo, both Japanese, and I'm sure there are people with every initial from A to Z in between. So what I've shown you in the first half of this lecture is how computers can illustrate, I hope in a striking way, what's happening geometrically. And in fact, in related work, it has been possible to conjecture new results and to prove new results as a result of seeing what happens on a computer screen. Now, in the second part of the lecture, what I want to do is to take a number of examples where there has been interaction between computers and geometry. Not all interactions in the same direction. I shall start by talking a little bit about profiles of surfaces, and I can illustrate that very simply by means of a couple of very simple surfaces, one of which I've got here is a football, which is just a sphere. And what I want you to look at is not the details of the illumination of the football round here. I want you to look at its outline, which of course is just a circle. What you see, the outline of this surface, is just a circle, and it doesn't really matter how I orient it. What you see is always a circle. Of course, you see a moving circle if I move it, or you see nothing much happening to the outline if I just rotate it. Here's another convex object, that is a rugby ball, which is no longer spherical, and this time the outline does change shape as you look at it from different points of view. The outline from this point of view is more or less circular. The outline from this point of view is more or less oval, and you get different outlines in between as I move it around. Now I'll take a slightly more interesting shape. I can show you over here. Just remove this. Here is what I would call a torus, which you might equally well call an anchoring or a donut. And the outline, as seen from where you are looking, from directly above, consists of two circles round here. It's two circles. If I tilt the torus somewhat, then the outline consists of still two ovals around here. If I tilt it further, then something is definitely happening to the outline at these two endpoints. And if I tilt it further, then we get a very interesting phenomenon, because there is a point here which really, some points along here which really we ought to call part of the outline. So let's just think of the right way to describe this. What we should say is that at points of the outline, for instance at points along here, the surface appears to be folding away from us. This is a way that we could describe this. The surface appears to be folding away from us at all the points of the outline. And that is also true at points down here. The surface is actually folding away from us at these points. And if the torus were made of glass, we'd be able to see behind here there were also points folding away. With this portion of the outline would continue behind. So something has happened to the outlines as I change from here where there are two circles, and now certainly this is something different because we appear to have something, part of the outline here and another part which, well, it either just stops short or perhaps it goes behind and does something else. Now I shall look at this again on a sequence of slides which are computer-drawn simulations, if you like, of tilting a torus. Here's looking at the torus from directly above. We'll now tilt it a bit and we have two ovals. We'll tilt it a little bit further, and this is the point at which something interesting seems to be happening because there are two pointy bits at the top and the bottom of this central part of the outline. At this point I'll pause a moment in this sequence and point out that there are more interesting things happening than you would actually see on a solid object like the one I was showing you a minute ago. If the object is actually made of glass so you can see through it, there will be a lot of points in the middle here at which the surface is folding away from us, which is the criterion that we're going to use for points of the outline. Here, if we look at this part of the outline in the center, the dotted parts are to be regarded as those which you'd only see if the torus was made of glass and you could see through it. But nevertheless, these are points of the surface where the surface is folding away from us. The solid parts of this outline are those which we can actually see and where the surface is folding away from us. In the next sequence of slides, all of this curve, all of this outline will be drawn in solid. There won't be any dotted parts. So we're looking at the full mathematical outline, as we might call it, all the points where the surface is folding away from us from our particular point of view, and regarding as if the surface was made of glass and we could see through it to see the points behind where it's folding away from us. So as we turn, in fact, what has happened is that two cusps have appeared. And this is just like this swallowtail perestroika that we had a while ago, which occurred in a completely different context on the changing evolutes of a family of curves. So there seems to be something similar happening here. And if we move further, in fact, these cusps broaden out, and in the final slide, the cusps have broadened right out, and you might like to think what is going to be the limit of this sequence of pictures. In fact, the limit, if we just go back to the overhead, is going to be what you will see if you looked vertically down. Now, if you imagine that that's made of glass, where are the parts where the surface is going to be folding away from you? And there's going to be certainly a portion along here and a portion along there, but there will actually be a circle at each end. And that will be the limit of these turning outlines. Well, the interesting thing from the point of view of this lecture about these outlines is that they can actually give information about the shape of the object. And let's just look at the thing a little bit more mathematically. So on this slide we have a sort of kidney bean shaped object on the left, and on the right is its outline as it would appear if you were looking at it in the direction of that vector v, which is near the bottom of the picture. So this on the right is, as it were, the shadow, but we're picking out all the parts where the surface appears to fold away from you when you look at it in the direction v. We're picking out the entire mathematical outline of this surface. There are certain points, like the point near the top left of the sort of kidney bean shaped surface, where a tangent plane is drawn to the surface there, and when this is projected in the direction of v onto this image plane on the right, the tangent plane collapses to a line. The image of that tangent plane is a single line, and what this indicates is that the surface there is appearing to fold away from us as we look in that direction. And on the surface there is a curve of points, which on the slide is called sigma v. There's a curve of points where from the direction v, the surface appears to be folding away from us. And these are the points of the surface which project onto that plane, onto the profile or the apparent contour of the surface, or the outline, as I've been calling it. Various words, all of which are used synonymously here: profile, apparent contour, or outline. So any surface, together with any direction, we have an outline, which is what we see as the points on the surface where the surface appears to be folding away from us. And the structure of this outline can be quite complicated. It can have lots of cusps on it. And as we change our viewpoint, the cusps can merge in pairs in one of these swallowtail perestroikas, just like happened on the family of evolutes of a family of curves. Now, the interesting thing here is that from the way in which the outlines change as you change your viewpoint, you can in fact deduce information about the shape of the surface. In fact, I did some work on this a few years ago when I was visiting the University of Massachusetts with a colleague there, Richard Weiss, who works in the computer science department. And I was delighted to see quite recently, in 1990, some work which generalized this and made it much more robust, as they say, much more practical, was being done in Oxford by Andrew Blake and Roberto Cipolla. What they have done is to take this idea of measuring what happens to the outlines of a surface as you change your viewpoint, and actually using this to get useful geometrical information about the surface. This is one of the many ways in which we, as human beings, deduce information about the shape of surfaces. Of course, it's very far from being the only way. For example, here's another way in which we deduce information about the shape of a surface. I don't know why the right view is on the left and the left view is on the right, but that's the way the slide is. This slide, in fact, came from the University of Oxford, where they do a number of practical experiments. And all I want to point out now is that there are specularities, as we say, on this view, that is, bright points. There is somewhere or other a source of illumination, and what we are seeing is reflections of this source on the surface of the mug. And the picture on the left, the so-called right view, you notice the positions of the specularities are slightly different from those on the right. There is something like, if you look at the surface of the mug, there is a bright point at the end of a long vertical bright streak, and this bright point has moved away from the bright streak. This in fact indicates something interesting about the geometry of the surface at the point where they separate. It means, in technical language, that this is a parabolic point on the surface. So there are many ways in which the shape of a surface can be deduced from what's happening to different views of the surface. We might look at the way the outline is changing, or we might look at the way that the specular points are changing as we move around, and all of these things can be used to deduce things about the geometry of the surface. But what goes on in between is singularity theory, is mathematics. To take the family of outlines, or to take the family of specular points, or whatever it might be, and to use those to deduce information about the geometry of the surface. So this is an example where geometry helps people who are interested in computer vision in developing remote sensing systems. The next thing I'll turn to is a case where computers help people who are studying geometry. A while ago I talked about how minimum changes to maximum as we move along the normal to a curve. That is, if we measure the distance from a point on the normal to a variable point along a curve, then this distance changes from being a minimum to being a maximum as the reference point moves along the normal. Let's look at the similar situation for a surface. So on this slide we see a surface which I'm taking to have equation z equals ax squared plus by squared plus maybe higher terms, and I'm going to assume that 0 is less than a is less than b. then as we move along the normal to the surface at the point P0, then a similar calculation to what I did before will show, in fact, that the nature of the distance function from a point on the normal to the surface changes as we move along the normal. I'll just go to the overhead briefly. I won't go through the details of the calculation this time, but what one does is to write down the square of the distance from a point on the normal to a point on the surface, x squared plus y squared plus k minus z all squared. And then you use the equation of the surface to expand that, and then you do a little bit of mathematics. But all I'll do is to tell you what the answer comes to, that if the distance up the normal is less than 1 over 2b, then you get a minimum there. The distance has a minimum. So this is rather like the situation for curves. If you're close to the point P0 along the normal, then the distance from that point on the normal to the surface has a minimum at P0. On the other hand, if you're between 1 over 2b and 1 over 2a, then the distance has a saddle there. This means that it has neither a maximum nor a minimum. In fact, it has a maximum in one direction and a minimum in the other. On the other hand, if you're further than 1 over 2a, then the distance has a maximum. So if we return to the slide, this means that as we move along the normal, the distance changes twice this time. So not just once, like it did for surfaces, where it changed from minimum to maximum. Here it changes from a minimum to a saddle, which is neither a minimum nor a maximum, to a maximum. There are two changeover points on each normal to a surface. What this means is that if we take lots of different points on the surface, then we will have on each normal, we will have two changeover points, and these changeover points themselves trace out surfaces as the reference point P0 moves around the surface. So for each reference point P0 on the surface, we draw the normal there, we mark the 2 points where the changeover occurs, and these 2 points trace out two surfaces which sometimes come together as the reference point P0 moves around. It does not matter that I have assumed that A is naught is less than A is less than B in the equation of the surface here. If you take different choices of A and B, then all that happens is that you get different ways in which maximum, minimum, and saddle change from one into the other, but there's always two changeover points. These can, in exceptional circumstances, merge into a single point at a so-called umbilic on the surface. But in general, there are just two changeover points. Now, the structure of this focal set, as it's called, the focal set is what is traced out by these two changeover points as we move the reference point around on the surface. Each point on the surface has two changeover points on its normal, and these trace out the focal surface as the reference point moves around. And the structure of this focal surface reveals a great deal of very subtle geometrical information about the original surface. And the precise structure of this focal surface is really still in the process of being elucidated. Very recent work in 1989-1990 in the University of Newcastle by Bill Bruce and one of his students, Tim Wilkinson, has revealed new information about this, the structure of this focal surface, which was previously unknown. It's the so-called structure of its parabolic curves. And this is being investigated experimentally in Liverpool by means of a very high-quality graphics workstation. And what I like to do is to show you some pictures which come from this. And the striking thing about these pictures is that they might remind you of something that happened earlier, where I talked about a migrating cusp, which we can think of as tracing out a sort of cuspidal edge, and a change swallowtail perestroika, where we get a swallowtail surface. This shows part of the focal surface of a surface, The surface itself is out of view. This is just part of the focal surface, and the colouring has a certain significance, which I won't go into now. But as we rotate the surface, you can see there's a channel down the middle there, that in fact what this surface is precisely a line of cusps, a cuspidal edge. Every section of it, as we see it now, every section, vertical section, will be a cusp. As we rotate it round, this is nothing other than a cuspidal edge, which is just like the time view of a migrating cusp in the plane, where we spread out the cusps in the time direction. But this has come from a different geometrical context, where we are looking at the focal surface of a surface. This is also the focal surface, part of the focal surface, of a surface which is out of view. What you see is part of the focal surface, and as you can see it rotating round, in fact, it's nothing other than a swallowtail, just like we saw a while ago from the time sequence of evolutes of a family of curves. So moving from front to back, as the surface appears now, moving from front to back sections will just be start off with two cusps, and these cusps will disappear as we move, as we change the section. As it is now, it would be sections from right to left. It's very remarkable that the same surface appears whether you consider a family of curves or a single surface. I'd like to conclude by showing what are really just some beautiful pictures which were produced by the University of Massachusetts in Amherst, where they're very interested in the structure of minimal surfaces. Well, I say they're just beautiful pictures. In fact, there's very, very interesting and subtle and difficult mathematics which goes on behind them, but I'm only going to talk about the pictures now. I'm going to talk very briefly about minimal surfaces. A minimal surface is a surface which has a saddle shape at each point, and the minimum curve along the top of the saddle, and the pass, if it was a mountain it would be a pass, the maximum point, are equally curved. This, in technical language, is to say that the mean curvature is zero everywhere. A not very practical way of thinking of this is that minimal surfaces are locally like soap films. That means that if you were to make a small hole in a minimal surface at any point, then dip it in soap solution, the soap film spanning that hole would in fact coincide with the piece of surface which you removed. Now, some very exciting research was done in the mid-80s at the University of Massachusetts when Bill Meeks and David Hoffman solved some equations for a new minimal surface which had been written down in quite difficult form by Costa a little bit earlier. And Jim Hoffman, no relation of David Hoffman, who is an expert at writing computer graphics routines, wrote some graphics to draw this surface. What they were interested in is this new surface which had been discovered, is it embedded, as the expression is? That means, does it lie in three-dimensional space without any self-intersections? And it was clear from the pictures that were drawn that in fact this surface was symmetric. This was completely unexpected. Nobody had thought that the surface was symmetric. Having seen that it clearly was symmetric, they went back to the equations and they saw, after a lot of calculation, that, goodness me, it was symmetric. It was in fact consisted of 8 congruent pieces. They were able to prove that each of these 8 was embedded, that is, did not self-intersect, and they were able to go on to prove that the whole surface was. And in this way, they were able to discover a whole new sequence of minimal surfaces. These minimal surfaces have interesting connections with polymer chemistry, by the way, where two polymers, that is, chains of identical molecules, each of them occupies a region of space, and it seems that for largely chemical reasons, the surface where these two chains of molecules overlap, in fact, is likely to be a minimal surface. And the kind of minimal surface which has come out of the research in the University of Massachusetts is the kind of candidate for this surface which occurs naturally in chemical copolymers, that is, polymers where two different chains of molecules are involved. So I'll conclude by showing you some of the beautiful pictures which have been produced at the University of Massachusetts. This is a minimal surface which has been known for a long time. It's called a catenoid. This is another minimal surface called a helicoid, which has also been known for a long time. This is the original example produced by Costa, and then Meeks and Hoffman looked at it in detail, and they saw from the computer graphics that it was symmetric. Incidentally, it doesn't actually stop along those three circles. It spreads out to infinity, but if you drew that, of course, it would obscure the rest of the surface, so it's been cut off. But at no stage does it self-intersect. Here is another example, another so-called three-ended example. The third end, that is the third circle, which is really where it goes off, spreads out to infinity, is actually hidden beneath. This is a four-ended example. That is, in the picture there are four circles where it stops, but in actual practice, in actual fact, it spreads out to infinity, but without ever self-intersecting. And here, finally, is a very beautiful picture of an infinite-ended minimal surface.